So now we're trying to look at our L4. We will try to see it this way, that we know that L4 consists of a to the power 2n, where n is greater than 0. This is our question. And P is the string, J is the pumping length, and R is the length of Vx. We know that. So our opponent decides the J part. So he decides the J. And let's assume he decided J to be 4. And we decide P. And in that case, the initial string, I pick a power of 2 that is bigger than or equal to J. Since J is equal to 4, let's pick n equal to 4. So that length is 2 to the power 4, which is 16. And my string becomes P equals to 16, which is 16 A's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And the opponent tries to apply U, V, W, X, Y. And we decide the I part. How many times we'll pump it. The pumping exponent. I pick I equals to 2. Now, we see that this is our setup. So we choose the initial P of the length as this. For example, the opponent chooses J to be 4, and we decided that 2 to the power 4, 16. And our P is A to the power 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And the opponent decides the split. Now we need to understand that what is P? So the P is a physical string that we decided. In our language, we had a to the power 2n, n bigger than 0. This is what we know. And it means that the total number of a's is a perfect power of 2. For example, if n was 1, it becomes 2 to the power 1, which is 2 a's. If it becomes n to the power of 2, 2 to the 2, it becomes 4 a's. And if it was n to the power 3, it became 2 to the power 3, which is perfectly 8 a's. 2, 3, 4, 5, 6, 7, 8. So 2, 4, 8. And n to the power of 4 would be 2 to the power of 4, which is 16 a's. And how did 16 come? The opponent went first and picked the pumping length, and they decided J to be 4. And now it's our turn to pick the string. And the pumping says that the string length must be greater than or equal to the opponent length, meaning that the P that we decide should be greater than or equal to the J that he will decide. So look at the allowed power of 2 to find one that is bigger than or equal to 4. Can we pick n equals to 1? The length 2? No, we cannot do it, because 2 is smaller than 4. Can you pick this one, n to the power of 2, where length is 4? Yes, we can pick it, because 4 is bigger than or equal to 4, which he choose. So we can do that. Can you pick n equals to 3, where length is 8? Yes, you can do it, because it's bigger than or equal to what he chose. And that's the same thing for 16. We can choose it. In our specific example, we choose to set n equals to 4 to give us a length of 16. That means our initial string can be 16. This is totally allowed word. This is possible. We can choose it. We can choose any word, but it just needs to be bigger than or equal to the J. You can technically choose any power of 2 as long as it's bigger than J. And that's how we did it. Now in this case, the intention was to understand this, to make you understand how is J and what is this situation. Now, of course, in our case, we don't know J. We never know it. Instead of picking a number, what we would do is that we would say, okay, P equals to a to the power 2J. This is what we know. Now, using our games, we can say, is 2J a perfect power of 2? Yes, it is. Because it is written as 2 to the power of something. Is the length P greater than or equal to J? Yes, because 2J is greater than equal to J for any positive integer. And now look at how algebra replaces 16 to or 33. So our original string was this. The next allowed string or a valid string would have to be P A2J plus 1. That would be the next valid string. And the opponent splits the string, pumps it to once, I equals to 2. This adds their pump length R to their strings. Which means that if the opponent split the strings and pump it once, this adds their pump length. So they are pumping it. Whatever UVW they decompose in, they choose, this will be part of the string then. And then this becomes R. For example, our new length becomes 2 to the power J plus R, with what they will add. This is the next one. Next, but this is what they will add. Since the rules state that the opponent pump cannot be bigger than window R less than equal to J, the absolute biggest length they can possibly make is maximum length would be 2 to the power J plus J. Because we know that J is only strictly smaller than 2J, we can do this algebraically, and we know this. Now we understand this concept, we can then move forward to understanding how all of this is working in real world. Because we know that the length of U is equal to A, and the length of V is double A. And because we know that J is always strictly smaller than 2J, we can do this algebraic step where 2J plus J is less than 2J plus 2J is equal to 2 multiplied by 2 to the power of J, 2J plus 1. You can say so. Because we already understand this specific step, we can just basically say that U is equal to A 1 2 3 4 5 6. V is 1 2. The part that gets pumped, W is basically nothing. X is AA, and Y is 1 2 3 4 5 6 7. 7 is 1 2 3 4 5 6 7. 7 8 9 10 11 12 13 14 15 16 17. Sorry, 16. Our initial A was 16, and that's the A distribution. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. There is an extra one, I think, somewhere. Yeah, there is an extra. So based on that, we know that these are the two parts that will get pumped. Now let's check. If we say UV, the length is equal to 2 plus 2 equals to 4, we can say this is completely legal because R is basically less than equal to J, and 4 is less than equal to 4, and R is also bigger than 1. All of these conditions satisfy. So in that way, we can just pump the new A's, and our new string should be 20 after we pump these 2 times. Of course, it's obvious. We add 2 more extra, then the new length should be 20. And why we win against all split is because that the condition fails that only allows whose length are perfect powers of 2. But look at the power of 2 around our neighborhood. When 2 is 4, it becomes 16. When 2 is 5, it becomes 32. The absolute next valid length allowed in the language. Our new pump string has a length of 20. Is 20 a perfect power of 2? No, it's not. It is trapped in an empty gap between 16 and 32. And what if the opponent chooses a different split? What if they made r equals to 1? So the new length becomes 16 plus 1 equals to 17, which is not a power of 2. So I still win. And what if they make r equals to 2? Then 16 plus 2 is again 18. That's still not a power of 2. Because opponent maximum pump size r is legally capped by j, which is 4, the largest length they can possibly generate is 16 plus 4, which is 20. They're physically too short to jump across the massive gap to reach the next valid length, which is 32. So the next power of 2 would be 32 after that, which they can never reach. And in this way, every single split keeps length trapped between 16 and 32. 16 and 32. And they can never reach this 32. And all valid split fails the condition. So the opponent has 0 safe moves. Now let's look at a different question. Now we have for regular languages, we have the question that a to the power n b remains the same, c to the power n, where n belongs to the natural number. And we know that it's very obvious to us that we have a UVW in this case, UVW, where we can say that the opponent chooses the j again, and let's assume he chooses 3, and we get to decide the p, the initial length of the string. I get to select a string where the language n is bigger than equal to j. Since j is 3, let's choose n equals to 3, and our string becomes a to the power 3, b remains the same, c to the power of 3, which is of course 1 2 3 b 1 2 3. So we have 2j plus 1 equals to 7. So we have 2j's, a to the power of j, b remains the same, c to the power of j. We have 2j and plus 1 is this, which is the length that we have in any case, whatever he does, equals to 7. So we can see 1 2 3 4 5 6 7. This is 7. Now based on that, they must follow the split. They decide the split again, and I decide the I side. And based on that, looking at the string, the first 3 characters are all A's. Therefore, no matter how opponent slices the string, the pumpable V is guaranteed to contain only A's. We know that the string always starts with A's. So the opponent chooses J3, for example, and I choose an initial length P of length 7. Based on that, the opponent tries to split it, and they must pick a split where U and V are less than equal to 3, and V is greater than equal to 1. Since the 3 letters are AAA, they have no choice but to take A's for their pump. They choose this split. U, and then V, and then W is the rest of. Now let's check the R. V is 2. We know V is 2 just like we see. And this is perfectly legal because R is bigger than equal to 1, and U and V, the window of this, is equal to 3, which is less than equal to Now, what happens is that because we pumped that V part, once we do it, we set I equals to 2, and if we I set is equal to 2, A plus AA plus AA plus A, B, C, 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 this becomes 2, B, 1, 2, 3. And A becomes 5, B become 1, and C become 3. Now the language rule states that the number of A's must perfectly match the number of C's. Because 5 is not equal to 3, the balance is completely broken. And what if the opponent chooses a different split? If they choose a split where R equals to 1, V equals to A, pumping yells 3 plus 1 equals to 4 A's, I still win because 4 is not equal to 3. If they choose a split where R equals to 3 is V equals to triple A, pumping up yells 3 plus 3, which is 6. And 6 A's are not equal to 3. I still win. Because the rule UV less than equal to J forces V to consist exclusively of A's, pumping up only increases the number of A's while leaving the number of C's completely unchanged. Every single valid split is physically trapped inside the first block of A's, and all valid splits fail the condition when pumped, and the opponent has no safe escape, and the regular language is broken.